before we jump into our next topic, which is going to be normal approximations of binomial distributions, and that's as hard to say as it sounds like it is, I figured we should probably go back and do a quick review of z-scores specifically, as well as normal distributions, just so that you're ready to actually move into that topic. So just in case you don't remember, normal distributions were the ones that looked like this, the bell curve. And you remember we broke it down into pieces, and we went 1, 2, and 3 standard deviations above the mean and 1, 2, 3 standard deviations below the mean. And our z-score was really just another way of saying how many standard deviations are we above or below the mean. So a z-score of 1 means we're 1 standard deviation above the mean. A z-score of -3 means we're 3 standard deviations below the mean. And then we had our little equation here to calculate z-scores given things like our x bar and our sigma. So before we go too much further, dig through your stuff and see if you can find your z-score table. I'd mentioned back at the beginning of the course we were going to need these again. If you can't find it, go print one off. These questions are going to be hard to do without one. Unless, of course, you memorize the z-score table, in which case, please come take my job. Okay, let's just, we're not going to go through like a full lesson. If you really need a full lesson, again, just go back and watch, I think it was 1.6 and do that one again. This is just going to be a kind of a quick example to try and refresh your memory of what we did a little while ago. So for our example, we have the mass of an average adult house cat is 4.8 kilograms with a standard deviation of 0.7 kilograms. What is the probability that a cat chosen at random is under 5 kilograms? Okay, well, we've got our z-score. We can calculate our z-score, I should say. Z equals x minus x bar. Now the x is the value in question, and then for part A, that's 5 kilograms. X bar is 4.8. That's our mean or mathematical average. And then on our bottom, our lowercase sigma, that's our standard deviation, which is 0.7. Okay, so once I've done that, I pull out my calculator and I say 5 minus 4.8 divided by 0.7 is 0. Now, my calculator says 0.2857. However, if you recall, z-scores, we need 2 decimal places every time. We don't want more accuracy or less. So I'm going to actually round that properly to 0.29. Okay, now is where I pull out the z-score table, which you're going to have in front of you, and I'm not going to bring up on the screen, but look for 0.29 on your z-score table. So 0.2 in the left column, and then read across to 0.09. And the place where those two things intersect is 61.409%. So that means that we would expect 61.409% of cats to be under 5 kilograms, which makes sense. That's a little bit above the average, so it should be a little bit more than 50% of the data. For part B, what is the probability that a cat chosen at random has a mass of over 6 kilograms? Okay, so we approach this one the same way almost. We say z equals x minus x bar. In this case, the x is 6 instead of 5. And so when I pull out my calculator, I get 1.2 on the top divided by 0.7 on the bottom is 1.74. And then I use that on my z-score table, look up 1.7 in the left column, read across to 0.04, and I'm getting 95.907. And just a reminder that in much the same way we did for part A, the percentage we get from the z-score table is always below. It always represents the amount of data below. So 95.907% of cats will be below 6 kilograms, which means that 100% minus 95.907 are going to be above 6 kilograms, and that number works out to be 4.093%. Now, just a little reminder, and this idea is kind of important or going to continue to be important. We said that there was a certain percentage of data below and a certain percentage of data above. Some of you might be thinking, well, that doesn't take into account the percentage of cats that would be exactly 6 kilograms. And I have to remind you that when we're talking about continuous data, so anytime that the data we've got is continuous, it is impossible to get any data point that is an exact value. So what you're really talking about is what percentage of cats weigh six kilograms down to an infinite number of decimal places. And the possibility of that is 0. So we're not going to find any cats that are exactly 6 kilograms. We may find lots that round off to 6 when we round with whatever degree of certainty we want, but we never find any that are exactly 6. Any single value is impossible to get with continuous data. Okay, and then the last part, little picture of Garfield at the bottom there. What is the probability that the cat chosen at random is between 4 kilograms and 4.5 kilograms? So we set this one up the same way we've done the others. Our x is 4 and 4.5, so we're actually going to do 2 z-scores, one for the 4, one for the 4.5. And when I punch that into my calculator, negative 0.8 divided by 0.7 is negative 1.14. Again, be careful you're rounding properly on those. And then 4.5 minus 4.8 over 0.7 gives us negative 0.43. Now you recall I'm using arrows here and not equal signs because z-scores and percentiles are not equal to each other. They're just related to each other through the z-score table. So using an equal sign and then writing a percent, negative 1.14 is not equal to a positive percent. It just corresponds to it on my table. So when I look up negative 1.14, I'm getting 12.714%, assuming that I'm reading it correctly, and it's always possible that I'm off by a row or a column. I will try not to make that mistake, but yeah, we'll see what happens. And the other one, negative 0.43, I'm getting 33.360%. Okay, and just a super quick reminder that when we have data like this, the 4 would be somewhere like here, and the 4.5 would be somewhere like there. This is by no means to scale or proper, but if this part of my data is below 4.5 and this part of my, let me change colors again, this part of my data is below 4, then the difference of them is the part between the two. So that's exactly what I'm going to do. I'm going to say big percentage minus small percentage. And when we plug that into our calculator, we get 20.646%. Okay, so approximately 1 in 5 cats, or 20%, are going to be between 4 and 4.5 kilograms. If my data is anywhere close to accurate, and I made it up, so who knows. Just before we move on, I am going to remind you that normal distributions are for continuous data only. So they apply to continuous data. They are not used to represent discrete data because we can't plug in numbers like 4.5. Obviously, cat weights are continuous, but like the number of cats wouldn't be. And I also want to point out that all the distributions other than the normal distribution so far that we've looked at, the uniform distribution, the binomial, the weighting times, the hypergeometric, those are all for discrete data where we're looking for a number of successes, which is always a whole number. So what we're going to be doing in the next lesson is trying to use this method for continuous data and force it onto a discrete data type of set, a binomial. And of course, there might be some tricks to that, but that's for the next lesson. So if you feel like you're ready now, there's no homework questions from this. This was just a reminder. You can continue on to the next lesson, and hopefully it goes well. We'll see you there.